Okay, so this is for me the first video I've recorded since paternity leave, so hopefully my brain still works. Yeah, so in this lecture we're just going to do more examples of simply supported beams, and you want to refer to the previous lecture for a revision, but obviously we'll talk our way through it. Okay, so we're probably going to look at least two examples in this little lecture. So what I got here, a light beam. The light doesn't really mean anything. The light just means that it satisfies the assumptions for these equations. That's all. Span 4 meters is simply supported. So when you're doing a question, you're going to want to zoom in on this. This is very important. So in terms of picture, you're thinking something like this. At the point x equal to 1 meters, that means 1 meter along the beam from the left hand side. There is a point load of 36 kilonewtons. Yeah, now it's probably a small remark at this point. This is not kilonewtons per meter, this is kilonewtons, but the UDL is kilonewtons per meter. Because this is, remember, is kind of infinite as such. Okay, between the points 2 and 4, there's a UDL of 30 kilonewtons per meter. And as we've said before, if it goes to the end of the beam, a UDL, you do not have to turn it off. And we have a couple of questions. We'll probably just talk through the questions briefly there. So solve m double dash, the second derivative of the bending moment is equal to minus load per unit length to find the bending moment in terms of step functions. Now, step functions just means these heaviside functions and these Macaulay brackets. Now, it's very important that you write square brackets for these. So some students were submitting work with round brackets. No, it's not. Like round brackets doesn't mean anything. It's square bracket. These aren't. This is like f of x. The deflection y at any point in the beam is found by solving this. So we're going to solve this differential equation for the bending moment, and then we're going to sub in that solution here and antidifferentiate this twice to find the deflection at any point. And then finally a question, what is the deflection of the beam at x equal to 3? And what that's about really is you understanding what these square brackets actually mean. Okay, so I'll recommend a picture. So I'll draw a little picture. And we're going to emphasize the simply supportedness. I'm not too interested in rollers, and that's not too important to me. Like, I won't even draw them here. You can draw them if that's the proper practice from your structural engineering. For me, it's just important that I see this triangle crack. Hopefully the pencil comes through reasonably well. Now like this actual beam that I'm drawing is probably longer than 4 because this is 0 and x equal to 0, this is x equal to 4. So it's between the supports is all I'm saying. We don't worry too much. Like basically what you're having, if we're kind of being a bit fussy, like this is a tiny little short, something like a cantilever. Well, it's not even a cantilever because it's not fixed, but it's something like that. And there's no loads in it, it just doesn't matter. Okay, so we can call this A and B if we want. And if we want, we know that this is where x is equal to 0. Sure, we may as well draw something. Now this would be, we're going to draw the loads here. So this would be the, more or less the W. Well, I shouldn't actually draw it in there. But that is where x equal to 0. That's where x equal to 4. And what are the loads? So at x equal to 1, so that's 1 along the beam. And you can do, your style of, I think some you do like 1 meter, 1 meter, 2 meters. That's all fine. This is a point load of 36 kilonewtons. And then a UDL between 2 and 4. And as we said, because it goes to the end of the beam, you don't have to turn it off. Now I'm drawing them like this, but remember they're actually kind of straight over that portion. Okay, so often what students will do here is they'll do the second derivative of the bending moment is equal to minus load per unit length. I think you're better off writing down the load per unit length first. So the load per unit length, what have we got? Well, we have a point load at x equal to 1, and the point loads are deltas. So that's, and I'll just write plus. You don't really need to write a plus, but I'll write it there. 36 times delta x minus 1 plus, because there's another load. What was the magnitude of this yoke? 30 times u, and it turns on at 2, and there's no need to turn it off. As UDL goes to the end of the beam, there's no need to include this, as this term is 0 for any point on the beam. Okay, so what we need to do is we need to solve the second derivative of the bending moment equal to minus this. So we're looking at second derivative of bending moment is equal to minus this. And if you've minus the sum, they'll both be minus. And now, through practice, you'll remember stuff like what is the antiderivative of a delta function and a u function, what is the constants that arise. So to solve this, it's very straightforward, just antidifferentiate both sides. Now, it's very important that you get the notation right. A few students are sending me work where like they're kind of leaving this out. Trust me, you need to get the notation right, because what happens is you'll start antidifferentiating and you'll kind of lose track of where you are. Like in the cantilever, we're going to be anti-differentiating 4 times. If you're not sure what thing you're at, you have an issue. So I really insist on getting the notation right. It is very important. It's not just a style thing. It's not just a communication thing. It's to help you keep track of your calculations. So we're going to antidifferentiate this. So the second derivative is the first derivative. Antiderivative delta function is a u function, and antiderivative of a u function is a square bracket. And the constant we pick up at this point is Ra. So here we go. So we'll go from the second derivative of bending moment to the first derivative equal. Fix the constant minus 36. My voice might go a bit funny because I haven't done any lectures. The delta goes to a u. Fix the constant minus 30, the u goes to a square bracket. And every time we antidifferentiate, we pick up a constant, and the constant here is Ra. Okay, so now we'll antidifferentiate again. Now what you want to be able to do is kind of do these calculations. I mean, there's no time exam, but you're not going to be wanting to be all day at them. But you want to be accurate, you want to be precise, and you want your answers to make sense, most importantly. So we go again from the first derivative to the function we're looking for. Antiderivative of u is square bracket. Fix the constant minus 30, and recall that the square bracket, for the purposes of antidifferentiation, just behaves like a power. So it's just like a power of x. So it's just add 1 to the power, divide by the new power, like that. Now, the other thing I was seeing is people doing a number of antidifferentiations and then putting in the constants. I don't really like that. I think you should every time put in the constant, because if you forget the constants, you don't really know what you're doing. Your answer is rubbish and you're not going to go well. So I recommend putting in the constant every time rather than leaving that out and putting in plus Rax plus Ma. Now, you can get away with it, but why not do things properly? So what do you have to differentiate to end up with a constant Ra? Well, if you think of it as Ra times 1, Ra times x. And we pick up a second constant here, which is Ma. Now we refer to the engineering. What I mean by that is the geometry, the physics. At A, the bending moment is 0. So if we're simply supported, it's like this. There's nothing causing the beam to bend here. Now, the loads are, but not the support. In contrast to fixed ends, where there is a bending moment at A, where the wall on top actually causes the beam to bend. So from now on, I'm just going to say, stated more or less as a fact. We've kind of explained it so many times. For simply supported, now it's only simply supported, the bending moment is 0 is 0, and the bending moment is 0 is what we call Ma. And yeah, and then over here, the bending moment here, now I'm just going to write down this, it's at 4, but I'm just going to write it L, the span is also equal to 0. And the idea is you've got 2 equations, you should be able to find 2 unknowns, and the 2 unknowns are Ra and Ma. Now it's very easy for simply supported, the Ma is 0. Now, so I'm just going to, if you do that for fixed ends, you're going to be entering a world of pain, because it's not equal to 0 for fixed ends, only for simply supported. Okay. So the first boundary condition implies that Ma is 0. Now we apply the second one that says that the bending moment over here similarly is 0. So what we're going to do is we've got the bending moment at x equal to 4. So what I'm going to do is I'm going to substitute x equal to 4 into this, and I know I get out 0. So I get equal to minus 36 square bracket x, which is 4, minus 1, minus 30. I could have done the 30 over 2, really. Yeah, maybe we'll do it. Let's call this 15. 30 divided by 2 is 15. And to run the x there is 4 minus 2 squared plus RA times 4 plus MA, which is just 0 anyway. So I'll just write plus 0. Now what you have to is I think it's even one of the learning outcomes, understand, I won't go back and find it, it's basically understand what a differential equation is. Understand that the solution of a differential equation is a function. And in this case, the solution of this is the bending moment at any point x. So this is the bending moment at any point x, and you can put in whatever value of x you want. And we know, in particular, at x equal to 4, you get out 0. So this is the bending moment at 4, and we know that this must, and I'll put in this exclamation mark to kind of emphasize the must, it has to equal 0. Okay. And now we've got a little equation in RA, which we can solve. So I think we'll take our time with it. So let's find some numbers. So square bracket of a positive number is just that same positive number. So this is square bracket of 3, that's just 3. 3 by 36, or by minus 36 is minus 108. This is square bracket of 2. Square bracket of a positive number is just itself. So that's just 2 squared is 4. 15 by 4, 60. Plus 4 times RA equal to 0. Now one of the things, you're in third year now. Now I know you had a very tough last semester with the COVID, and it's not much easier now, but the odds are you're a bit more mature now, and you're going to properly actually do your maths. And what's going to actually kind of come and bite you is the fact that, well, the new maths you're able to do, you know, the latest maths and the complicated stuff that we're going to get into, very basic stuff is going to kind of hold you back. So I'm always going to kind of take our time and do the basic stuff right. So, for example, solving equations, this is a thing that people mess up all the time. So here I got at minus 168. I'm trying to find RA on its own. So what I should do is get rid of the minus 168. And to get rid of the minus 168, you apply the inverse, which is adding 168. So I'm going to add 168 to both sides here. So I'm thinking of two numbers are equal. If I do the same thing to both of them, they'll still be equal. And the plus 168 minus 168 is 0, and 0 plus 4a is just 4a. And then the 0 plus 168 is 168. And okay, it looks like moved it over, changed the sign, but that's not actually what's happening. Now you're going to get, by the way, the baby crying and the dog barking. There's nothing I can do about it. I'm not going to go and edit the videos. We'll just pause and make sure that the baby isn't drowning me out or whatever. Right, now we've got RA, want to get on its own, it's multiplied by 4. So what is the inverse of multiplying by 4? Dividing by 4. And what we do is we divide both sides by 4. So RA multiplied by 4 divided by 4 is just RA, and 168 divided by 4 is 42. And you could put in the units there if you wanted of kilonewtons, but it's not going to be a big deal. Error rule for the cracking. It's not really a big deal because you don't put the units into this. The idea is that the kind of, I don't know, the 42 kind of carries the unit or whatever. Okay, so we want to present our answer. So the other thing that's very important is, like, when you find R and MA, that's grand, but you want to go back and write down your answer. And this is your answer, but just put in the R and the MA. So here's the minus 36 square bracket, blah, blah, blah. 30 divided by 2, the 15, spot on. RA times x, 42 times x plus 0. You don't try it in there. Okay, so that's question 1 done. And if we wanted to find the bending moment at any point, say for example at x equal to 2, you substitute in x equal to 2, that'll give you the bending moment at that point in terms of kilonewton meters. Alright, what's next? What's next is we want to find the deflection. That's how much below the neutral the surface of the beam is as such at the point x. You have to solve this differential equation. Now EI are just constants, E is Young's modulus, I is to do the beam, and the idea is that you can change the beam out. Now keep the same length, keep the same loads, and the answer doesn't change that much just by a factor of 1 over EI, which we'll see later. But what we have to do is write EI times second derivative deflection equals bending moment, which we just found. So that said EI times this equal to bending moment. Now we antidifferentiate twice again. So again, this is where the notation is very important. You're antidifferentiating both sides. So you're antidifferentiating this. Now it's a constant times something. So fix the constant. And the antiderivative of the second derivative is the first derivative. I'm freely moving between the dash notation and the what's called the Leibniz notation with the d's. That shouldn't be an issue for you. So now fix the minus 36. Sorry, the space is going to be a bit small here. And then antiderivative of square bracket. Well, we've seen this above. It behaves like x to the 1. It'll be squared over 2. Fix the minus 15. And antiderivative of square bracket squared is square bracket cubed over 3. Well, that should still be 2. Cubed over 3. Fix the 42. And what is the antiderivative of x? Well, it's x to the 1. It'll be x squared over 2. We're going to be careful with that in a moment. And we pick up a constant, and the constant here we call C1. Okay, and we go again. So maybe I'll come back here. So again, we're antidifferentiating both sides. Fix the EI. And the antiderivative of the first derivative is the original function y of x. Now what I'm going to do, and I have to for the purposes of space, is simplify these constants. Apologies for the coffee. So the 36 over 2 is 18. So I'm going to fix the constant minus 18. And then I got square bracket squared. Antiderivative is square bracket cubed over 3. Then the 15 over 3 is 5. Now the numbers don't necessarily have to be nice here. Your engineering lecturers might use decimal places. I'm usually going to want to use fractions. If you are going to use decimal places, maybe use 4 significant figures. We're going to learn a bit more about rounding error in the final chapter. See where it's safe, when it's not safe. So 15 divided by 3 is 5. And then antiderivative of square bracket cubed is square bracket to the power of 4 over 4. 42 divided by 2 is 21. And the antiderivative of x squared is x cubed over 3. The antiderivative of a constant c1 is c1x, and the other constant we pick up at this point is c2. Okay. Now we're going to learn a bit more as we go through. You're going to kind of get used to things, but the c2, as long as it's fixed on the left-hand side, or supported even on the left-hand side, be it simply supported, fixed ends, or if you have a cantilever that's free on the right, the C2 is always going to be 0. And that's always going to be the case in Maths 7019. Now, we'll just, more or less, we'll just kind of, not prove it, but just argue it here. And we'll probably do it later, and we've possibly done it previously in previous lecture. So we know, what else do we know about these things? So we know that the deflection here, so the deflection is when the beam goes below the neutral. It happens everywhere, but at the span, the deflection is 0. It can't go below the neutral at the support. Like, say if this is your beam, and say look at 2 there, it goes below the neutral, but this bit doesn't. This doesn't go down at all. So here and here, the beam doesn't bend. Now if we apply the initial condition, it's called our boundary condition because the boundaries y of 0 equals 0. Let's see what happens. So if we were to substitute x equals 0 into both sides, because these are true for all values of x, so sub in x equals 0. We get EI times y of 0. Y of 0 is a deflection at 0. That's 0. So if you substitute x equals 0 into both of these, this bit is 0. Okay. Now this will give you the square bracket of 0 minus 1, the square bracket of minus 1. What you have to remember, very important, is the square bracket of anything that is negative is 0. So if you put x equals 0 into that, that's 0. Similarly, if you put x equals 0 into that, 0. It doesn't matter that it's the power of 4 because you do the thing in the bracket first. And the square bracket of 0 minus 2 is the square bracket of minus 2, which is 0, and 0 to the 4 is 0. So that'll be 0. Put x equals 0 here, you get 0. X equals here, you get 0. So all you're left with is the C2. And if you remembered, if you put x equals 0 over here, you get EI times 0, which is 0. So you get 0 is equal to 0 plus 0 plus 0 plus 0 plus C2. C2 must be 0. But this is always going to be the case in Math 7019. So you can kind of get used to that. Now, C1 is not. So we need another piece of information to find out what C1 is. Okay, we may as well say something here that C2 is equal to EI, and this will always be true in Maths 7019, times the deflection at 0. So it doesn't actually matter what E and I are, it's multiplied by the deflection at 0, and the deflection at 0 is always going to be 0. Okay. The C1, and we'll see this a bit later, if you put x equal to 0 into both sides here, you're going to get a square bracket of a negative, square bracket of a negative, they're both 0, 0 squared, that's 0. You get EI times the slope at 0. Remember, the first derivative is the slope, so C1 is EY times the slope at 0. So what this means is that C2 is proportional to the deflection at 0, which is always 0, and C1 is proportional to the slope at 0. Now the slope at 0, if it's fixed ends, the beam is going to come out straight. So for fixed ends, we're going to say that C1 is 0. But if it's simply, that's what fixed ends looks like. If it's simply supported, the beam is going to look like this, and this is a negative slope. So what we're going to expect to see for simply supported is that C1 is negative. Okay, so let's see. Yeah, so this is an example, right? You write down the maths. You can make a little mistake in your equation. If you get a positive C1, that means the beam looks like that. That's wrong. So what you want to do in that case is, well, in an exam situation, you just say, look, I know this is wrong. I have to move on. But you're going to be doing assignments, so it's going to be a little bit different. You're going to have time to fix it. That's the coffee gone now. Right, so anyway, let's do this y of 4 equals 0. Where's that coming from? The deflection of the beam on the right end is 0. So let's go. So you get EI times deflection at 4 is equal to. So I get minus 18 over 3, that's minus 6. Now all I'm going to put in here is it's actually, I better put it in, okay, square bracket 4 minus, I definitely have to put it in 4 minus 1 cubed minus 5 over 4, and I can't simplify that. So your engineering lecturers probably do 1.25, but if they had a third, they might do 0.33, which I don't like because you got rounding error, but we'll talk about that later. Chapter 4. 21 over 3 is 7 times x, which is 4 here, cubed, plus C1 times 4. And we've already said that C2 is 0, so I don't need that. And now, what have we got? The deflection at 4, as we've said numerous times now, that's actually 0, so EI times 0 is, so 0 is equal to this. And rather than writing the 0 here, let's write the 0 here. Okay, now I'm going to go into the calculator, which is rare enough. Well, no, maybe there. Look, we'll see where we are. Now the things in the square brackets here are positive, and when the thing in the square bracket is positive, they're just normal brackets. Otherwise, what makes them different from normal brackets is if the thing in the bracket is negative, they spit out 0. So let's go. Minus 6. Now something I don't want to see is people putting 4 minus 1 into the calculator. Come on now. It's just 3 cubed minus 5 over 4 times 2 to the 4, which is 16, plus 7 by 4 cubed. I'm getting 266. So 266 plus 4 times C1 is equal to 0. And let's finish this off properly. Take away, we've got a plus 266. So how do you get rid of a plus 266? You do a minus 266 to both sides, and you end up with 4C1. 0 minus 266 is minus 266. And then to get rid of that, multiplied by 4, we should do a divided by 4. And what's important here is that I have my minus. If you want to put it in decimals, that's fine. That's no problem. The units of that are God knows what. Probably could actually be, I mean, it's slope, so it's like it's I think it's millimeters per meter, something like that. Okay, and then we have one more question. What is the deflection of the beam at x equal to 3? Oh, we never presented our answer, so we should do that. So we'll just about have time to present our answer. So I'm going to do it in two goes. So I'm going to write this down. Okay. Minus 18 over 3 is minus 6. Minus 5 over 4. X minus 2 to the 4. 21 over 3 is 7. C1, and as we said, it has to be minus. If that comes out positive, you made a mistake. For simply supported, minus 66. Oh, I prefer the 133, but these are equal. There's no rounding error there, so it's not the end of the world. Right. Now, the question was solve this differential equation. The solution is y of x. So I want to get y of x on its own. I need to get rid of this EI. Now, I've multiplied by EI, and what you can do to get rid of multiply by EI is multiply by 1 over EI. Because if you multiply this by 1 over EI, you'll have 1 over EI times EI, which is EI over EI, which is 1, and 1 times y of x is y of x, the EI is gone. So multiply both sides by 1 over EI. And you should present your answer. We must multiply the right-hand side by 1 over EI as well, like that. That's what I recommend. And now the question was the deflection at x equal to 3. I just have to sub in x equal to 3 into this. Because this is the deflection at any point, and we're interested in at x equal to 3. I'm running out of time now in the video. I better go really fast. I'm going to go a little bit faster here because I'm going to run out of video. 3 minus 1 is 2. 2 cubed. Minus 5 over 4. 3 minus 2 is 1. 1 to the power of, that's 1. Plus 7 times 3 cubed. Minus 66.5 times x, which is 3. Apologies. And the answer will be in terms of EI. So I got minus 6 by 8, minus 5 over 4. What? Yeah. Plus 7 by 3 cubed is 27, isn't it? Yeah. Minus 6.5 by 3. And I get minus 239 over 4. And it's also divided by EI. And so the answer is in terms of EI. I might run out of time here. It's no bother. I don't really mind. As E gets bigger and I gets bigger, this number gets smaller. So this deflection gets smaller as E and I get big. E being big is big Young's modulus. That means that it's a stiffer beam, and larger I means kind of a larger cross section.